Welcome back to the deep dive. Today, our mission is all about statistical integrity. It's about closing that huge gap between just reporting a single number and reporting a truth you can actually bet on.
Exactly. We've spent time figuring out how to get that single best guess, what we call a point estimator.
Right. For things like a mean, a probability,
Yeah.
a standard deviation.
But the moment you go public with that one number, say, our market success rate is exactly 33.6%, you're creating, an illusion of certainty.
It's a false precision, isn't it?
Yeah.
That single point, it suggests zero error, absolute perfection, and that's almost never true in the real world.
It's not. If you're drawing information from a sample, there's always going to be some random error. So we need to move on from just stating one guess. We need to define a scientific sort of security zone around it.
And that's the goal for this deep dive, then.
That's the goal, to build a tool that quantifies this security. It's called the confidence interval.
The framework that lets us say, okay, the true value is, with a high degree of probability, somewhere between this number and that number.
Precisely, between X and Y.
And to show you why this is so much more than just some abstract exercise, we're going to dive right into a practical problem, a real dilemma for a modern business.
Yes, the NetBank scenario. It's a classic case all about brand awareness.
So picture this. NetBank, it's an online financial institution, and they want to gauge how well-known they are. They commission a big market survey.
A pretty standard one. They poll 1,000 people.
So our sample size, our N, is 1,000.
And out of that sample, the number of people who actually recognize the brand our success count, K, is 336.
Okay, so the point estimator for their brand awareness is pretty simple to calculate. It's just K divided by N.
So 336 divided by 1,000, that gives us 0.336.
Or 33.6%, and that is the best single guess we have for the true proportion for P.
But the marketing manager is smart. They get sampling. They come back to the stats team and say, look, 33.6% is nice, but I have to make a multi-million-dollar decision with this. I need to know the true range of our awareness.
And here's the kicker.
Right. They say, and I demand 99% certainty before I pull the trigger.
That 99%, that gamma, as we call it, equals 0.99. That single requirement changes everything. We're not just looking for the center of the data anymore.
No. We are now tasked with finding a scientifically defined safety margin. We call it C.
So we're building an interval around our estimate, 33.6%, that goes out C in both directions.
The interval is going to be our estimate minus C up to our estimate plus C.
Yeah.
If the manager only wanted 50% certainty, that interval would be tiny.
And if they wanted 100% certainty.
Then the interval would be from 0 to 100%, completely useless.
So this is the trade-off. Our whole focus today is figuring out how to calculate that specific margin, C, that gives the manager exactly the 99% confidence they've demanded.
It's all about quantifying that sweet spot between security and precision.
And we're going to start by tackling this for yes-no type data, which is all governed by something called the binomial distribution.
So our NetBank survey data, we model it with the binomial distribution, BNP. We know N is 1,000. We saw K is 336. But PP is the unknown we need to pin down.
Okay, so the fundamental condition we need to satisfy is this. The probability that the true actual value of P falls inside our interval.
Our estimate plus or minus C.
That probability has to be at least 0.99.
Right. And this sounds simple enough, but you hit a paradox almost immediately.
We want to start with the inequality. Our estimate N minus C is less than or equal to P, which is less than or equal to AN plus C.
And the paradox is that P, the true probability of brand awareness, is a fixed unknown constant. It's not a random variable.
It's just some number out there in the universe that we don't know.
Exactly. And in classical statistics, you can't assign a probability distribution to a fixed constant. You can't calculate the probability that the constant P falls in some range. The whole setup it gets stuck.
So we can't calculate PPs in the interval directly. Okay, this is where we need a trick, right? The different way of looking at it. How do we unlock this?
The trick is a conceptual pivot. It's realizing there's a deep mathematical equivalence happening here.
Okay.
If the true probability P is close to our observed proportion carry-on, well, that's the exact same thing as saying that our observed hit count, xk, is close to its expected count, which is np.
Oh, I see. So we don't know the distribution of the constant p,
Right.
but we do know the distribution of our random variable, x, the number of hits we saw. X follows that binomial distribution.
Precisely. So we have to algebraically rearrange the whole Inequality, we need to get the unknown constant p out of the middle and into the margins and get our random variable x, the thing we know about, isolated in the center.
Okay, let's walk through that pivot step by step because it feels like the conceptual heart of this whole thing.
It really is. It's the key to all confidence intervals. So let's start with the upper bound. P is less than or equal to kn plus c.
Okay, the true probability is less than our estimate plus the margin.
To start isolating k, we multiply the whole thing by n. So now we have np is less than or equal to k plus nc,
And then just rearrange it to get k by itself.
which gives us npn. Nt is less than or equal to k. That's our lower boundary for the count k.
Makes sense. And now for the other side of the original inequality, knc is less than or equal to p.
Same process. Multiply by n, you get knc is less than or equal to np.
And rearrange that one. K is less than or equal to np plus nc.
Right. So now if we combine those two results, our entire objective has shifted. We're no longer trying to pin down the unknown constant p.
We're now trying to calculate the probability that our randomly observed count, xk, falls within a specific interval.
An interval defined by np, nc, and np plus nc. So what's the probability that our actual sample result is within n units of what we theoretically expect it to be?
Wow, that's a huge leap. We've pivoted from p constant in an interval to pre-lane random variable in an interval.
And that second one, we can actually solve because we know the distribution of x. So our new goal is to find a c that makes this true. PNP-NC equal x NP plus NC is greater than or equal to gamma.
Okay, so now we have a solvable probability problem, but it involves the binomial distribution. And working with that for a sample size of 1,000, that sounds awful. You'd be summing up hundreds of individual probability terms.
It would be incredibly tedious, yes. Which is why we bring in a powerful tool for simplification, the de Moivre-Laplace theorem.
Right, because our sample size n is large. 1,000 is definitely large.
It is. So we can very accurately approximate the clunky discrete binomial distribution with a smooth, continuous normal distribution. This is absolutely crucial for any practical calculation.
We're basically switching our model to the normal bell curve, n mu sigma 2. And in this case, the mean mu is np, and the standard deviation sigma is the square root of np1p.
Exactly. So to calculate the probability we need, we standardize our boundaries. We turn NP-NC and NP plus NC into z-scores.
And that means we can use the standard normal tables, the ones with the function phi. The standard process is you take your value, you subtract the mean, and you divide by the standard deviation.
And now watch how the math rewards us for that careful algebraic pivot we did earlier. The expected value of x is mu NP.
Okay.
So when we calculate the z-score for the upper boundary, NP plus NC, the numerator is NP plus NC mu.
And since mu is NP, the NP terms just cancel out. They vanish.
You're left with just NC in the numerator. It's beautiful.
And I'm guessing the same thing happens on the lower boundary. The numerator is NP-NC. The NPs cancel, and we're left with just NC.
That's it. And the standard deviation in the denominator is sigma. So our whole probability condition simplifies down to this. Phi of minus phi VO if it's sigma has to be greater than or equal to gamma.
The mean, the NP term that was causing all of trouble, it has completely dropped out of the equation for finding the width of the interval.
That's why the pivot was so important. It lets us isolate the effect of our safety margin, C, relative to the statistical noise, sigma, and makes the whole thing solvable with standard tables.
Okay, now we need to solve that equation for C.
Right, and for that, we use the symmetry of the Gaussian bell curve. The probability of being below some negative value min to z is the same as 1 minus the probability of being below positive z.
Or phi vela 1 by v.
So when we substitute that property back into our equation, it simplifies again. We get 2 phi sigma 1 is greater than or equal to gamma.
And that looks much easier to solve. We can just isolate the phi term.
We can. A little algebra gives us C phi sigma has to be greater than or equal to 1 plus gamma 2.
That term on the right, 1 plus gamma 2, that's the specific area under the curve we need to cover to get our desired confidence level.
It is. And to finally get C out of there, we have to apply the inverse function, phi 1.
Which is the quantile function.
And the quantile is just the z-score that corresponds to that required area. Let's call it z gamma. So now we have the relationship. NC sigma must be greater than or equal to z gamma.
And solving for our safety margin C is now just a simple rearrangement.
C has to be greater than or equal to sigma n z gamma. And that is our guide for calculating the width of the interval.
Okay, we have the formula for C, but wait a second. We've hit another wall.
We have.
The standard deviation, sigma, is defined as the square root of NP1p. That formula still has p in it.
Yes, C still depends on P, which is the very thing we're trying to estimate in the first place. We just swapped one dependency for another.
So what do we do? This seems like a classic chicken and egg problem.
It is. It's the second classic statistical dilemma in this process. And since we can't know the true P, we have to estimate that variance term, P1P, using the data we have.
Okay, so what's solution number one, the most practical one?
The most practical, straightforward solution is to just substitute our point estimate, Kn dash the 0.336 cents and fourth, inside that square root.
Okay, that seems simple enough.
It works pretty well, especially with a large sample size. But it does mean our calculation depends on the specific result of our one sample, and it doesn't offer an absolute mathematical guarantee that the interval is wide enough.
So what's the safest approach? The one that guarantees we meet that 99% confidence level no matter what?
That's what we call the worst-case scenario solution. We take a close look at that product, P1P. This term represents the maximum possible variance, or scatter, in the underlying data.
So we need to find the value of p that makes that term as large as possible.
Right. And when you think about it, when is a binary outcome, a yes or no, most unpredictable?
When it's a 50-50 shot, like flipping a fair coin.
Exactly. When P is 0.5, the outcomes are as uncertain as they can possibly be. And mathematically, the term P1P is maximized at 0.50.5, which is 0.25.
So the square root of that term, square 1p, is maximized to the square root of 0.25, which is just 0.5.
And by using that maximum possible value of 0.5 in our calculation for sigma, we are essentially calculating the largest plausible standard deviation. It ensures our confidence interval is conservatively wide.
We're building in a safety buffer.
Yes. We replace sigma in our formula for C with score Bn 0.25, which is score Pn2.
And when we substitute that worst-case sigma back into our formula for C, what does it look like?
It simplifies into this beautifully clean, practical rule of thumb. C has to be greater than or equal to 1/2 score Bn Z gamma.
And that formula, it only depends on the sample size and the safety level we want, which determines the quantile Z gamma. The specific result, the Kn, is gone.
It's a safe harbor approach, used all the time in planning studies or when you absolutely have to guarantee the confidence level under any circumstances.
All right, let's put this powerful formula to the test for NetBank. We have n equals 1,000 and gamma is 0.99.
First step, we need the quantile for 99% certainty. So
Yeah.
we look up the area, 1 plus 0.992, which is 0.995 in the standard normal table.
And that 0.995 quantile is a classic number in statistics. It's Z gamma equals 2.58. That's our safety multiplier.
Now for the denominator in our simplified formula, 2 score TRN. So 2 score G1000.
Okay, the square root of 1,000 is about 31.62, so the denominator is roughly 63.24.
So our safety margin C is just 2.58 divided by 63.24.
Which works out to C being approximately 0.0408.
A safety buffer of about 4.1 percentage points on either side of our estimate.
Our point estimate was 33.6%, so the 99% confidence interval is 0.336 plus or minus 0.0408.
Right, which gives us a final range of 0.2952 to 0.3768.
So now the marketing manager can go to the board with a statement that is rock solid.
Completely defensible. They can say, based on our sample, we are 99% confident that the true brand awareness rate in the population lies somewhere between 29.5% and 37.7%.
And that's a statement that accounts for uncertainty, for risk. It transforms that one shaky number into a real decision-making tool. It's a whole different ballgame from just saying 33.6%.
It tells you exactly how much wiggle room you have.
Okay, so we've really unpacked the discrete yes-no binomial case. Now let's pivot to the continuous world, which is really dominated by the normal distribution.
Right. Think about measurements like height, weight, temperature, or tensile strength. Data that can take on any value in a range, not just a count of successes.
The core principle is the same, though, right? We have a set of measurements, and we need to wrap a statistically sound interval around our best guess.
Exactly. An interval for the true mean, mu, or maybe for the true variance, sigma 2.
Looking at the decision tree for this kind of data, there are a few paths. We could be missing mu or sigma 2 or both.
To keep things clear and build a foundation, we're going to focus on the simplest, cleanest case, case 1A.
We're finding the interval for the mean mu, and this is the key assumption. We're assuming that the true variance, sigma 2, is already known.
Maybe we know it from decades of historical data, from a stable manufacturing process, for example.
So we have n measurements, x1 through xn. We know they come from a normal distribution, and we know sigma.
This scenario is the foundational building block.
So our best point estimator for the true mean mu is just the sample average, x bar.
Yes.
In the binomial case, we had to approximate its distribution with the normal one using that de Moivre-Laplace theorem. What makes the normal case so much cleaner statistically?
The normal distribution has this wonderful cooperative mathematical property. If you add up a bunch of normally distributed variables, the result is also perfectly normally distributed.
Ah, so because the sample mean x bar is just a sum of those measurements divided by n.
Right. It means that x bar isn't an approximation. It is exactly a random variable that follows a normal distribution.
That's a huge difference. We don't need a large n for the means distribution to be normal.
We don't, though, of course, a large n makes our estimate much more precise.
And do we know the parameters of this distribution for x bar?
We know them exactly. Its expected value is just the true mean mu. The mean of the means is the true mean.
And its variance, it's not the original variance sigma 2, is it?
No, and this is critical. Its variance is the original variance divided by the sample size. So Vx bar is sigma 2n.
And the standard deviation of that sample mean, we call that the standard error, is the square root of that.
Sigma squirt nn. This formula perfectly illustrates the law of large numbers. As you increase your sample size n, the variance of your estimate shrinks. It gets more and more precise.
But it shrinks proportional to the square root of n, which means to cut my uncertainty in half, I don't just double my sample size.
You have to quadruple it. The returns diminish, but the gain in precision is very real.
So now we have our random variable, x bar, and we know its distribution is n mu, sigma 2n. We're ready to find the interval for that unknown center, mu.
And the logic is identical to what we did in the binomial case. We start with the goal. The probability that the true mu is in our interval x bar c, x bar plus c, must be at least gamma.
And we use the exact same algebraic pivot. Instead of talking about the true constant mu being near our random measurement x bar,
We pivot. We talk about our random measurement x bar being near the true constant mu.
so we calculate p mu c x bar equals mu plus c is greater than or equal to gamma.
Exactly. And now we standardize the boundaries to use the standard normal tables. We subtract the expected value of x bar, which is mu, and we divide by the standard error, sigma squared n.
And just like before, for the upper bound, the numerator is mu plus c mu. The mu's cancel out. Same for the lower bound.
It's the same beautiful simplification we saw before, but it's even cleaner because we didn't need any approximation to get here. The z-scores only depend on c in the standard error.
The condition becomes 2, c sigma squared n, 1, use gamma.
We solve that for c using our friend the quantile z gamma.
And that leaves us with a final clean formula for the safety margin c. Take the standard error, sigma squared n, and you multiply it by the quantile z gamma that matches your confidence level.
That's it. So the entire confidence interval is x bar, sigma squared n z gamma, x bar plus sigma squared n z gamma. This formula is the absolute blueprint for estimation in this domain.
And this formula is so powerful because it's where the statistics meets the real-world constraints of engineering or business. The width of our confidence interval, how precise we can be, is completely controlled by 3 factors.
The 3 levers, as we call them, the only things that dictate the size of that margin.
Lever number 1, the sample size, n. It lives in the denominator, under a square root.
So if you increase n, the denominator gets bigger, the whole standard error term shrinks, and your interval gets narrower. It's the statistical answer to uncertainty. Just measure more.
And this is usually the cheapest lever to pull, isn't it? The cost of just collecting more data is often less than, say, overhauling a machine.
In many cases, yes. Though we have to remember that square root, going from a sample of 5 to 50, is a huge improvement. Going from 1,000 to 1,001 is barely noticeable. There's a point of diminishing returns.
Okay, lever number 2. The standard deviation, sigma. This is the inherent noise or variability in the system itself. It sits right in the numerator.
This is the hard one to change. If the thing you're measuring naturally scatters a lot, sigma is large. And a large sigma directly makes the interval wider. High uncertainty requires a wider net.
So if a manager wants to reduce sigma, they can't just run another test. They have to actually improve the process, buy better equipment, use better raw materials.
Correct. Reducing sigma usually costs serious capital. It's an investment in process quality, not just in information gathering.
And finally, lever 3, the confidence level, gamma. This is all about risk tolerance, and it controls the quantile, z gamma.
Right. If the boss says 95% certainty isn't enough, we need 99%. Well, the quantile jumps from about 1.96 up to 2.58.
That's a big jump.
It is. And that 30% increase in the multiplier directly widens the interval by 30%. If you demand more security, you have to sacrifice precision. You cast a wider net to be more sure you've caught the true mean.
So it's this fundamental trade-off. Security costs you precision, all three levers, your budget for data, N, the quality of your system, sigma, and your appetite for risk, gamma, are all intertwined in this one elegant formula.
That's it exactly.
Let's make this concrete. Let's apply this model to that plastic foil manufacturing scenario. The company needs to certify the tensile strength of their product.
Okay, so we assume the strength is normally distributed. And from historical data, we have a known variance, sigma 2, of 25,600 newtons squared.
Which means a standard deviation, sigma, is the square root of that, so 160 newtons.
They run a new quality check with a sample size of N50. The average strength they measure, X bar, is 2,400 newtons. And management demands a high safety level. Gamma equals 0.99.
So we'll just follow the formula step by step. First, the standard error.
That's sigma square OTN, so 160 square T50.
Square root of 50 is just over 7, about 7.07. So the standard error is roughly 167.07, which is about 22.6 newtons.
And notice how much smaller that is, 22.6, than the standard deviation of a single foil, which was 160. That's the power of averaging.
Next, the quantile. For 99% confidence, we already know that Z gamma equals 2.58.
So the margin of error, sir, is just the standard error multiplied by the quantile, so 22.6 times 2.58.
And that works out to C being approximately 58.4 newtons.
So our final interval is centered on our measurement of 2,400 newtons. It's 2,400 plus or minus 58.4.
Which gives us a range of 2341.6 to 2458.4 newtons.
And that's the critical output. If the safety regulations require a minimum average strength of, say, 2,300 newtons, the quality manager can be extremely confident.
Right. They can report that even the lowest likely value for the true average, 2341.6, is comfortably above the minimum. And there's only a 1% chance they're wrong about that range.
And think back to the levers. If the manager was unhappy with that nearly 60 newton margin, they could quadruple the sample size to n equal 200, which would cut the margin in half, down to about 29.
Or they could argue for accepting 95% confidence instead of 99.
Which would immediately shrink the margin down to about 44 newtons, just by changing the quantile from 2.58 to 1.96.
They're constantly doing that cost-benefit analysis. More data versus more risk. And the confidence interval gives them the language to have that exact conversation.
It does.
But that was the clean case. Let's talk about the real world for a second. In a brand new factory, you often don't have decades of historical data telling you what sigma is. How often is the variance really known?
Almost never in new applications. The much more common scenario is case 1b.mu is unknown, and the variance sigma 2 is also unknown. It has to be estimated from the exact same small sample you used to find X bar.
So instead of the true fixed sigma, you have to plug in the sample standard deviation, S.
Correct. And you are replacing a known constant with a second random estimator, S. And while S is our best guess for sigma, it's inherently noisy, especially with small samples.
So if we just plug that noisy S into our formula and still use the normal distribution tables, we're introducing extra uncertainty that we're not accounting for.
That's the danger. You would be systematically underestimating the true margin of error needed. Your 99% confidence might in reality only be 97% confidence. You have to compensate for that extra uncertainty.
And how do we compensate?
We shift from the normal distribution to the t-distribution, which is also called the student distribution.
And what does the t-distribution look like compared to the normal bell curve?
Imagine the bell curve gets squashed down a little in the middle and the tails get puffed up. It's a fatter curve. That extra probability mass in the tails accounts for the higher chance of extreme outcomes when you're estimating the standard deviation.
So to capture 99% of the area under that fatter curve, your boundaries, your quantile, have to be pushed farther out.
Exactly.
Yeah.
The required quantile from the t-distribution is always larger than the one from the standard normal for the same confidence level. This makes the confidence interval a little bit wider.
The necessary price you pay for estimating that second parameter.
It is. And the shape of the t-distribution actually depends on your sample size, n, through what we call degrees of freedom.
So for a very large n, does it just become the normal distribution?
It does. As n gets huge, say over 100, the t-distribution basically merges with the standard normal, because S becomes a near-perfect estimate for sigma. But for small samples, using the t-table is absolutely mandatory.
And just to close the loop, if we were trying to estimate the variance itself,
Then you leave these symmetric distributions behind entirely. For variance, you use the skewed chi-square distribution. But the core concept, The bedrock of all this remains the same.
Estimator plus or minus a safety factor.
Always. Whether that factor comes from the normal, the t, or the chi-square table, you're always just building a protective shell around your best guess to honestly show how reliable it is.
This has been a journey into, really, statistical accountability. We started with that single best guess, the point estimate, and we've built up to the confidence interval, the piece of context that tells you how much weight your numbers can actually bear.
And that intellectual pivot we made, from worrying about an unknown constant to leveraging the known distribution of a random measurement, that is the centerpiece of this entire field. It turns an impossible problem into one we can actually solve.
So a key takeaway for you listening is to never settle for a single number when decisions matter. Always ask for the range and the certainty level. An interval estimate is an honest estimate because it shows its own uncertainty.
And we saw how that interval's width is controlled by those three levers: sample size n, your data budget, inherent variability sigma, your process quality, and confidence level gamma, your risk tolerance.
Let's circle back one last time to that plastic foil manufacturer. We calculated that for 99% certainty, they needed a 58.4 Newton margin of error. But let's imagine the margin is so wide that it sometimes forces them to halt production just to be safe.
That's the real-world cost of high security. Lost precision shows up as lost production, lost efficiency.
But if that company decided to lower their requirement to, say, 90% confidence, we know the margin of error would drop a lot, maybe to just 37 newtons. That narrower interval lets the factory run more efficiently.
But the price of that narrower, more efficient interval is risk. They are now accepting a 1 in 10 chance that the true average strength is actually outside that range and potentially below the safety limit.
So the final provocative thought we want to leave you with is this. In these high-stakes fields, medicine, engineering, finance, which cost is typically higher? Is it the business cost of being a bit less precise by using a wider, safer interval? Or is it the liability cost that comes with accepting a small but specific chance of failure by using a narrower, riskier one?
The answer to that question really defines the entire risk culture of an organization. Something to think about as you see estimates and polls in your own life.
Thanks for joining us for the deep dive. We'll see you next time.